Welcome you all for this session. Today's topic is complex low pass representation of band pass system. So here system is nothing but the channel is considered as the system which is having the impulse response of H of U, having the bandwidth of 2B, that is the narrow bandwidth channel plus or minus B, that is the bandwidth. So that is the 2B width of the channel is going to feed with the S of t, which is also a narrow bandwidth signal, having a 2W as the signal frequency and width of W plus or minus W hertz. So one reason is to avoid modulation. Why we go for modulation is the one of the reason is to avoid the crosstalk and interference of the signal. Okay, so for that reason we are going to convert the low frequency signal into high frequency signal, that is the band pass signal. So again here in this case we are converting band pass to low pass. Okay, next. So what is SFT? SFT is the narrow band signal. SFT is a narrow band signal. So SFT is the narrowband signal. Then it is Fourier transform as denoted as S of I, which is frequency is limited by plus or minus W hertz. Okay, with the carrier frequency FC, with the carrier frequency FC, and it is also assumed that the signal frequency, that is also assumed that the W is less than the carrier frequency Fc. That is it understood that the message signal is always in low frequency, whereas the carrier signal is in high frequency. So let us the signal S of t is applied to a linear time invariant. So what do you mean by linear time invariant? As I mentioned earlier also, it is nothing but the signal is not going to vary with respect to the time. That's why the time invariant systems. So with the impulse response of h of t and its frequency response of h of f. Okay. So assume that frequency response of the system is limited to frequency within plus or minus b, that is bandwidth of the carrier. The system bandwidth is 2b, which is narrower than equal to the input signal 2w. That is, the channel bandwidth is greater than the signal bandwidth, or else here in this case usually for communication system, okay, the channel bandwidth is greater than the signal bandwidth because the signal should be transmitted through a channel without any distortion. But in this case we are considering the system bandwidth, that is the channel bandwidth 2b is narrower than, or else it is equal to the input signal bandwidth 2w. Now represent the bandpass impulse response h of t in terms of quadrature component hi of t and hq of t. So by using the analogy of the representation of bandpass signals, we can also represent h of t in terms of its in phase and quadrature component as h of t is equal to hi of t cos 2 pi fct minus hq of t sin 2 pi fct. Okay. Next, so h of t can be represented in terms of complex envelope of the signal, that is complex impulse response of the system as the of the bandpass system. Since h of t we are going to considering as the channel or the bandpass system impulse response. So h tilde of t is equal to hi of t plus j into hq of t. So that is the equation 2. So we may write h of t in terms of that is the original bandpass impulse response of the system, that is h of t can be taken in terms of the complex envelope as h of t is equal to real of h tilde of t e to the power of j2 pi fct, whereas so hi, hq and h tilde are the low pass signal. We are converting high pass to low pass, having the frequency band from minus b to plus b. So we can also determine the complex impulse response, that is h tilde of t in terms of in phase and the quadrature components hi of t and hq of t. from the bandpass frequency of the response h of f as follows. So we can also write that is h conjugate of t be the complex conjugate of h tilde of t. We can write h of t is equal to real of h conjugate of t into e to the power of minus j 2 pi fct. So here actually while converting a band pass to a low pass, we are considering only the real terms, because band pass signal is going to transmit, it is going to transmit only the real signal, only the real signal, not the complex one. That's why wherever you are deriving the derivation, we are going to consider only the real part of it. So h of d is equal to real of s conjugate of t e to the power of minus j 2 pi fct. Now the equation 3 and comparing equation 3 and 4, this and this equation. So h of t, that is h of t is equal to 2 h of t. When adding the equation 3 and 4, it is going to 2 h of t and h tilde of t plus h conjugate tilde of t into e to the power of minus j 2 pi fct. So by applying the transform, Fourier transform on both the sides of the equation and using the complex conjugation property of Fourier transform, we get that is 2 into h of here in the last slide, that is 2 in place of h of t, we are going to convert that into a Fourier transform, that is h of t into e to the power of minus j 2 pi fct as h f of minus st, and h of t in terms of conjugate it as h conjugate of minus of f plus c. So now when you are going to multiply this sign to here, it becomes a minus f minus fc, and here h tilde of, here one more parameter is going to go on, that is h tilde of f minus fc plus h tilde of conjugate of minus f minus fc. So what the modification we have done for this, that is h of f is equal to the Fourier transform of h of t, h tilde of f is equal to the Fourier transform of h tilde of t. So now we using the that is what the real valued impulse real valued impulse response of h of t, which satisfies, that is h conjugate of f is equal to h minus f. This considering the duality property of the Fourier transform. So what is the complex conjugation property deal with? That is x of t is equal to the Fourier transform of x of t is equal to x of f is equal to the Fourier transform of h conjugate of t is equal to x conjugate of minus f. That is what we have done here, you can see. So h tilde of represents the low pass frequency response having limited to f greater than or equal to b and b less than or equal to fc. So h tilde of f minus fc is equal to 2 into h of only when we consider f is greater than 0 and eliminating the low that is f is less than 0. So considering the even symmetry, that is it is considered as the negative frequency. So this is the condition when f is less than 0. So we are eliminating, considering only the positive frequency signal. So now this is what the specified bandpass frequency response h of f corresponding complex low pass frequency response h tilde of is obtained by taking the part of h of f defined for positive frequencies. So only we consider the condition f is greater than 0, shifting to origin by scaling factor by amplitude by 2. So when what is h of f from this equation right here. So what is h of f? So h of f is equal to 1 by 2 of h tilde of t complex low pass signal h tilde of f that is f minus fc. So now this is what they are here the sentence is about, that is shifting to the origin and by scaling shifting it to the origin by scaling by 1 by 2 will give the h of f. So the complex response of h tilde of f can be decomposed into in-phase and quadrature component as this h tilde of f is equal to h tilde I f plus j hq of f. In-phase components can be extracted, that is h h tilde I of f is equal to 1 by 2 of h of f plus h conjugate of minus f. And hq of f is equal to h tilde of q of f is equal to 1 divided by 2j into h tilde of f minus h conjugate of f minus f. So finally, the complex impulse response h tilde of t is obtained by taking the inverse Fourier transform of h of f, that is h tilde of t is equal to h tilde of f e to the power of j2 pi df. So this is about the complex representation of bandpass system. Now the next slide is depicting about the bandpass signals and its system. So the bandpass signal S of t in terms of complex envelope S tilde of t. So S of t we are going to consider the real only the real part of the signal. So since I have told you the bandpass signal is going to transmit only the real part of the signal. So S of t is equal to real of S tilde of t into e to the power of j2 by fct. So the impulse response of h of t of the bandpass system is in terms of complex impulse response of h tilde of t can be written as, so h of t is equal to real of h tilde of t e to the power of j2 pi fct. So the above equation has a common multiplier, that is e to the power of j2 pi fct. In practically the factor accounts for sinusoidal carrier frequency fc, which facilitates the transmission of modulated bandpass signal S of t across the bandpass channel as the mid frequency as fc. It is nothing but the carrier frequency is going to be so that is fc while transmitting through a channel. The other one is the exponential factors complicates the analysis of the bandpass system driven by the modulated signal. Okay. So this analysis can be simplified through a combined use the complex low pass equivalent representation of both the modulated signal S of t and bandpass system categorized by the impulse response H of t. That's why we are going to convert that into a complex low pass equivalent, and the simplification can be carried out by time domain or frequency domain. What it is in the time domain procedure? With the complex representation of bandpass signal and system, we derive analytically the efficient method for determining the output of the bandpass system driven by the corresponding low pass signal. So as your assumption here is that the S of t denotes the spectrum of S of t and H of t denotes the spectrum of H of t. Okay, so both going to carry out the frequency, the same carrier frequency as Fc. So practically no need to consider the situation which the carrier frequency of the input signal is no aligned with the mid band frequency of the bandpass system, since we are going to consider the mid band frequency as Fc. Thus changing the carrier frequency input signal by the amount of del Fc, any changing in the carrier frequency del Fc, so the corresponding to the factor e to the power of j2 pi del of fct in the complex envelope of the input signal or the complex impulse response of the low pass system, still we can justify that assumption that S of f and H of f are both are centered around the same carrier frequency. Both are centered around the same carrier frequency. Okay. That is S of f, that is S of f, and both centered around the same carrier frequency Fc. Okay. So next, so what is X of t? X of t is the outcome of the system, that is which is going to have the bandpass signal as well as bandpass system. When you are going to combine both the signal, that is what you are going to feed a system, one system. Okay, this is the system having the impulse response H of t. Okay, and you feeding input here, it is S of t, here it is S of t, S of t, and taking it as a X of t. So what is S of t? S of t is the bandpass signal. What is H of t? H of t is the response of the bandpass system. Okay, so that is what the incoming bandpass signal is S of t, and X of t is the outcome signal. What is X of t? X of t is the real of X tilde of t into e to the power of j2 pi fct. So now how this H and S are related, that is X of t is equal to H of t convolved with h of t convolve with s of t, that is x of t. So x of t is equal to h of t convolve with s of t. This convolution can be write in the form of integration, that is x of t is equal to minus infinity to plus infinity h of tau into s of t minus tau into d tau. So in terms of pre-envelopes h of t, that is real of h plus of t and s of t as the real of s plus of t. So x of t is the limits are vary from minus infinity to plus infinity. We are going to consider only a real part of it, only the positive envelope. So by considering the basic property of pre-envelopes that described the following relation, that is h plus of tau into real of s plus of tau into d tau is equal to half of real of h of tau into h conjugate of tau. This is one of the property in the pre-envelope. So we are equating the equation to here. So what is the real part of it? Real part of this is going to be x of t is equal to half of real of minus infinity to plus infinity h plus of tau into s conjugate of tau into d tau. Now we have to make this equation is in equivalent in terms of complex envelope, in terms of complex conjugate signal. So for that, from the Fourier transform theory, that is s of minus tau, it is in place of s of tau as the efficient of removing the complex conjugation, as the effect of removing the complex conjugation. Why? We are considering only the real term, there is no complex term in the real terms. So because of that reason, we are modifying it by applying the Fourier transform, that is s of minus tau in place of s of tau has the effect of removing the complex conjugation. So by considering that, now the equation becomes, that is x of t is equal to 1 by 2 real of s minus infinity to plus infinity h of tau s plus t minus tau into d tau. When you are going to expand this using by multiplying with the complex exponential terms, so this equation becomes, when you are going to multiply the complex exponential term, so we take e to the power of j2 pi fct, fct tau outside, and e to the power of minus j2 pi fct. When you are going to multiplying here, then we get e to the power of minus j2 pi fct tau and h of tau into s of t minus tau. So here we know that this minus and the plus terms getting cancelled. So only the remaining term is x of t. So x of t is equal to 1 by 2 real of minus infinity to plus infinity e to the power of j2 pi fct complex conjugation of h of tau s of tau t minus tau into d tau. So by comparing the equation 1 and 5, the earlier equation, so we come to know that x tilde of t is equal to half of h tilde of t into s tilde of t minus tau into d tau, where there actually in place of x of t we are going to substitute here by comparing it, the exponential terms are getting cancelled. So these are the remaining terms. So the important of this relationship is the result of, that is the band pass function and the corresponding complex low pass function. That is the relationship between the band pass function. Okay, so this is going to be the band pass function and this is going to be the low pass function. The relationship between these two terms can be considered as x tilde of t. So this is the representation block diagram representation, that is input band pass signal s of t and a band pass impulse response as h of t and output signal x of t. Is now it is low pass complex envelope low pass signal. So now the complex envelope of input signal s tilde of t and the complex impulse response of h tilde of t and the envelope of the output 2x of t. So the input of the description of band pass system figure A and the complex low pass equivalent model for the band pass system. So you can compare here. So it is a scaled envelope of the output 2x tilde of t. So this can also be written as that is x tilde of t is equal to s tilde into s tilde. So where this symbol is indicating the convolution. So we'll take S of t in terms of in phase and the quadrature component. That is S tilde of t is equal to S of t plus J SQ of t, and H of t as Hi of t plus J HQ of t. So 2 into X tilde of t is equal to H of t plus J HQ of t convolve with S of t into J SQ of t. When you are going to multiply it with, so finally you are going to extract by neglecting the imaginary terms or the complex terms. That is 2 into x tilde of t is equal to 2 into x tilde of t is equal to hi of t convolved with si of t minus hq of t convolved with the sq of t, okay, and hi of t convolved with si of t plus um, plus okay. So we got the term as hi of t convolved with si of t minus hq of t convolved with sq of t. So now we can rewrite this as xi of t, and this as in terms of j, that is j sq of t. So now what is 2 x tilde of t? It is 2 times of xi of t plus j 2 times of sq of t. Okay. Next. So next xi of t in terms of so comparing the real and imaginary parts of equation 7 and 8. So we can write the in phase component as 2 into xi of t as 2 into xi of t as hi of t convolved with si of t minus hq of t convolved with sq of t. Similarly 2 into sq of t as j si of t convolved with sq of t plus hq of t convolved with si of t. So the now we got extracted in phase and the quadrature components of the complex envelope H tilde of t of the system. Outputs are obtained by using low pass equivalent model as shown in the figure. So this is what the extraction of signals with respect to the low pass signal. So you are feeding S1 of t and that is getting multiplied with Hi of t and HQ of t. Feeding SQ of t multiplied with HQ of t and Hi of t. So here at this point this low pass signal is represented as the summation plus and minus. Here the low pass signal is with the summation of both the parameters as plus. So this is the block diagram approach of a complex low pass signal. This gives the relationship between the in phase and the quadrature components of the response and the band pass system and band pass input signal. Okay. Hope this video is going to be informative for you. So we shall see in the next video regarding line coding. Thank you for watching this video.